Ever tried decoding a location clue like a small village 2 km north of a river? It's deceptively complex, and that's exactly why researchers are pushing the boundaries of AI to solve it. Today, we're exploring how cutting-edge models are learning to georeference text, transforming ambiguous descriptions into precise geographic coordinates. Let's break it down. Georeferencing isn't just about plotting points on a map, it's about understanding spatial relationships. Traditionally, this relied on explicit coordinates or clear place names. But what happens when the input is something like, near the old oak tree, south of the highway? That's where AI is rewriting the rules. The breakthrough hinges on large multimodal models, systems trained on both text and visual data. Think of them as AI cartographers, capable of reading descriptions and seeing maps. Their task? To parse a textual clue and map it to the real world. Here's the process. The AI first dissects the text using named entity recognition, NER, identifying key elements like old oak tree or highway. It then maps these entities to real-world features using contextual cues. For example, south of the highway triggers a spatial reasoning engine to calculate relative positions. This isn't just keyword matching. It's a layered analysis of geography, language, and scale. Next, the model generates a tailored map excerpt. Unlike generic satellite views, it dynamically adjusts to the description. If the text mentions a small village near a river, the AI zooms in on that area, highlighting landmarks and optimizing the grid size to avoid imprecise blob regions. This requires integrating data from sources like OpenStreetMap and Google Places, but with a twist. The map isn't static. It's a living, context-aware representation shaped by the text itself. The real innovation lies in how the AI synthesizes text and map data. Researchers tested methods like step-by-step reasoning and cartographic expert simulation, but the most effective approach combined logical deduction with explicit grid size parameters. By instructing the model to calculate distances in meters or prioritize linear features, they improved accuracy by over 30% in controlled tests. What makes this research groundbreaking? It's not just about better maps, it's about bridging the gap between human language and geographic reality. Imagine using 19th century field notes to locate a lost archaeological site, or analyzing climate data tied to specific textual descriptions. The applications span archaeology, environmental science, and even urban planning. But challenges remain. Linear features like rivers or highways can confuse models if the map lacks detail. And while systems like GPT-4 Vision excel at pattern recognition, they still struggle with nuanced spatial logic, like distinguishing north of a river from on the northern bank. These gaps highlight the need for hybrid approaches, combining AI with human expertise. So where are we headed? This isn't just about smarter software, it's about redefining how we interact with geography. As these models evolve, they'll unlock new ways to explore history, monitor ecosystems, and even navigate cities using only textual clues. Next time you encounter a cryptic location description, remember, AI is getting closer to decoding it. And who knows? Your next app update might use this tech to help you find that hidden cafe mentioned in a novel. No GPS required.